Hello, I'm Haneul Kim from III Excel Lab. Today, I will present the paper titled AnyPlace, Learning Generalizable Object Placement for Robot Manipulation, which was accepted to CORL 2025. The key question is, can a robot place objects precisely in unseen real-world environments? First, I will briefly explain what AnyPlace is and what problem it aims to solve. One of the biggest challenges in robotic object placement is that the precision learned in simulation often breaks down in real-world environments. There are two main reasons for this. The first is domain shift. Observation change due to differences in lighting, sensor noise, materials, and backgrounds. The second is object diversity. Even small variations in shape, scale, or context geometry can fundamentally change how an object must be placed. Placement is particularly challenging because it is not just about predicting a position. It requires estimating a precise 6DOF pose where two objects must physically align and make correct contact. Even small errors can lead to failure. AnyPlace addresses this by shifting the perspective. Instead of treating placement as a problem of global scene understanding, it reformates it as a problem of aligning local geometric structures between two objects. This change in viewpoint is the key idea. Based on this formulation, AnyPlace adopts a two-stage architecture. At the high level, a vision language model proposes possibly placement locations. At the low level, the model focuses only on the local geometric region around each candidate's location and predict a precise CE transformation. Importantly, although the model is trained entirely on synthetic data, it generalizes in a zero-shot manner to unseen objects in real-world environments. However, rather than converging to a single solution, it can predict multiple valid placement models, demonstrating a multimodal capability. Okay then, why universal placement is fundamentally hard? On the left, the buyer rack example has multiple holes, meaning that there are many valid placement targets. This shows placement is not about reaching one target, but reasoning about a set of feasible solutions. The first reason is geometry diversity. Objects have very different fundamental geometries, like handles, stems, holes, and dimensions vary even within the same category. So placement is not just position alignments. The relative pose that made contacts must be rediscovered each time. And second reason is multimodality. In most placement tasks, there isn't one correct answer. There are multiple correct placements. In this buyer rack, inserting into any of the 6 holes is valid, but if a model finds only one mode, it misses the others. By the way, existing methods have limitations. Many approaches require demonstrations or data for each object type, so new object force retaining or recollection. And global method can get stuck in local minima, repeatedly finding only one out of 6 valid holes, so they failed not just in success rate but in discovering diverse valid modes. The third limitation is the precisions vs generalization trade-off. So tight tolerance insertion requires sub-millimeters precisions, but global models lose precision when trying to generalize, and when pushing precisions, they often overfit to specific cases. So this paper does not attempt to solve the object placement problem with a single model. Instead, it decomposes the placement pose prediction into two stages. The left side, a high level stage, and right side, a low level stage. This coarse-to-fine decomposition represents the central design philosophy of the paper. Let me first explain the high-level stage. So the lore of this stage is to determine where to place the object. Object placement is inherently a multimodal problem. For example, if a viral rack has multiple holes, each hole can be a valid placement location. So existing models often fail to capture all possible models in such scenarios. They tend to converge to a single mode or repeatedly predict only a subset of possible locations. Therefore, the key idea in this stage is to define candidate placement location in 3 space and pass only the corresponding local regions to the low-level model. Given a task instruction and an RGBD image as input, the high-level VLM predicts possible placement locations in the image as a 2D key points. For instance, if the instruction is insert the wire into the leg, the model outputs multiple insertion positions on the rack as key points in image space. So these 2D key points are then projected into 3 coordinates using depth information. This allows the systems to define candidate placement location in the physical coordinate frame. Meanwhile, from the same RGBD image, language condition segmentations using SAM2 is applied to isolate the target object. From this segmentation, we obtain the point cloud of the objects to be placed, denoted as PC, this one, and computes its 3D bounding box. During the cropping step, we centered on its 3D placement key points and extract local regions from the basic objects. The size of this region is determined by the 3D bounding box of the target object. The resulting point cloud is denoted by PB crop, this one. So importantly, the target and the base objects are not merged. Instead, the goal is to simplify the problem by allowing the low-level model to focus only on the local geometric structure around a candidate placement location rather than the entire scene. As a result, the low-level model takes 2 point clouds as inputs, PC and PB cropped. And the cropped is to look, and it then learns the logical geometric relationship between these two objects in order to predict a precise placement pose. Now let me move on to the low-level stage. The goal of this stage is to predict how exactly should the objects be placed at the selected location. The problem is formulated as predicting a relative rigid transformation. The inputs are 2 points clouds. The objects to be placed, this one, and the cropped local regions around the candidate placement rotations, denoted as PP crop. The output is a rigid transformations, and this T in SE3 that aligns the target objects with the selected placement regions. So here, SE represents the group of rigid body transformations in 3D space, which includes both rotation in SO3 and translation. In other words, it corresponds to the 6 DUF transformations, 3 degrees of rotations, and 3 degrees of translations that aligns the object in space. The model consists of transformer-based encoder and a diffusion-based decoder. First, the transformer encoder extracts feature from the 2 point clouds. Each point cloud is processed with self-attentions to capture its internal geometric structure. Then, cross-attentions layer, this one, learns the geometric relationship between the two objects. The resulting features are pulled into the latent embedding. So conditions on this embedding, the diffusion decoder, this one predicts a small SE3 transformation at each time step. The predicted transformation is iteratively applied to PC, gradually moving the objects closer to the target pose. The final placement pose is obtained by accumulating the transformation predicted across all diffusion steps. During training, an L1 loss is applied to the translation component, and a geodesic distance is used for the rotation component. In addition, a chamfer loss is computed between the point clouds transformed by the predicted pose and the ground truth pose. By minimizing the sum of these losses, the model learns geometrically precise alignment. So the reason for using diffusion is that placement is inherently multimodal. A simple regression model tends to oblige multiple valid solutions, leading to incorrect poses. In contrast, diffusion models the distribution of possible solutions and can generate multiple precise alignments. However, since discrete placements models are already separated at the high-level stage, the low-level model only needs to handle continuous fine-grained refinements within each mode. Now I will explain how the predicted placement pose is executed by the real robot. So the output of the low-level model is the target placement poses. So however, the robot cannot simply telepose the object to that pose, right? So a full pick and place pipeline is required to physically grasp and move the object. First, AnyGrasp. This is used to predict how the target objects can be grasped. AnyGrasp is a grasp detection model that estimates a grasp pose. We can denote it as T-peak, indicating the direction and position from which the robot gripper can stably grasp the object. Next, CoolRobo. It is used to generate a physically executable motion trajectory. So CoolRobo considers the robot's kinematic constraints and potential collisions to plan the collision-free path that moves the objects from the grasp pose to the target placement pose. An important point is that the predicted placement pose T-place and the grasp pose T-peak are not always jointly executable. For some grasps may cause collisions at the target placement pose, or they may violate the robot's kinematic constraints. Therefore, the authors performs rejection sampling over the generated pose pairs. Multiple grasp candidates are tested, and only the combinations that are collision-free and physically executable are selected. In this way, the system ensures that the robot ultimately grasps the object and places it accurately at the desired location. So, in summary, AnyPlace proposes a coarse-to-fine architecture that explicitly separates placements model at the high level and predicts precise CE transformation based on local geometric structure at the lower level. This design enabled the system to address both multimodal exploration and fine-grained alignments simultaneously, and demonstrates that even when trained purely on synthetic data, the system can generalize to diverse real-world placement tasks. In this paper, the dataset is not merely a tool for evaluation, but the core components deliberately designed is to enable generalization. So previous works often relied on highly specific tasks and constructed datasets limited to those particular scenarios, like inserting a book into the bookshelf. While such approach may perform well on the task, they struggle to generalize to other types of placement problem. In contrast, the goal of this paper is not to build a model that just excel on single predefined task, but to construct a dataset that broadly represents the concept of placement itself. To achieve this, the dataset is designing around fundamental placement types such as stacking, hanging, inserting. So, a key insight is that the model focuses on local geometric relationship rather than the global scenes. Since the lower-level model only observes local regions, the dataset can concentrate on how two objects physically interact and align. This makes data generation more systematic and scalable. So, the data generation pipeline consists of two main stages. The first is object generations. Using Blender, a wide variety of 3D objects are procedurally generated, which parameters such as size and shape randomly samples to ensure diversity. The second stage is placement post-generation. NVIDIA Isaac Sim is used to compute physically stable placement pose. So for 3 configuration, the system automatically identifies stable placements. This enables the datasets to cover a wide range of placement scenarios commonly encountered in real-world setting. So for experiments, they aim to answer the following 3 questions. First is, how well does AnyPlace perform in terms of object placement, success rate, coverage, and precision compared to baseline model? And second, how does each component of AnyPlace affects the overall performance? And next, how well can AnyPlace generalize to novel objects and unseen configuration in the real world in a zero-shot setting, despite being trained only on synthetic data? The first metric is success rate. This does not simply measure whether a pose is predicted, but whether the object is successfully and stably placed in the environment. The second metric is coverage, which is particularly important. Instead of evaluating whether the model finds a single correct answer, coverage measures whether the model discovers all valid placement locations. The third metric is precision, which is measured only in simulation. It evaluates translation error and rotation error and compares against the 3 models. They compares against 3 models. The first is NSM, the neural shape mating. This is a traditional regression-based approach that directly predicts a single 6DOF pose from the inputs. The second baseline is RPDIF, a state of the SOTA global diffusion-based methods. It takes the entire scenes as input and generates distributions over possibly placement pose. And the third is AnyPlace EGM, EBM, energy-based variants of the proposed model. So this serves as an ablation study to test whether the diffusion-based decoder is essential, or whether a simpler scoring-based formulation would be sufficient. So this is not EGM, this EBM. And the experimental tasks include stacking, peg insertion, cup hanging, and buyer insertion. Now let's see the results. Starting with placement success. So the table 1 presents the success rates across 4 tasks. An important distinction here is between single mode task and multi-mode task. So in single mode task, there is essentially only one correct placement location. So, for example, stacking does not require extremely high precision. So all models achieve similar performance, like this. So, however, in such as peg insertions, these ones, which demands high placement accuracy, AnyPlace significantly outperforms the baselines. These improvements can be attributed to the low-level models, focusing on the local regions and performing precise SE alignments. The difference becomes more pronounced in multitask training. So in tasks such as cup hanging and buyer insertion, where multiple valid placement location exists, AnyPlace achieves a particularly high success rates, like this. And yes, in a buyer insertion task. In contrast, the baseline model shows a substantial drop in performance. All of this. So this result suggests that the high-level VLM effectively separates placements model, while the local level model performs fine-grained refinements within each mode. Moreover, even when using the same high-level module, the diffusion-based model outperforms the energy-based variant. This indicates that iteratively denoising in diffusion model is better suited for high-precision alignment task. Now let us examine placement coverage. The coverage measures how well a model captures all possible valid placement modes. So figure 4 shows how coverage changes as the number of samples increase. The left plot corresponds to the buyer insertion task, and the right plot corresponds to the hanging task. The red curves represents AnyPlace. So AnyPlace rapidly approaches near 100% coverage with only a small number of samples. This is because the high-level BRIG-LM explicitly predicts possible placement location, allowing the model to sample independently within each mode. In contrast, RPDF, the orange ones, fails to fully capture multimodality, resulting in relatively low coverage. Overall, these results demonstrate that the course-defined structurally addresses the multimodal exploration problem. And finally, let us examine placement precisions. So figure 5 shows the distribution of translation error and rotation error for the insertion task. A histogram concentrated toward the left indicates smaller errors. AnyPlace exhibits smaller and more consistent distributions for both translation and rotation errors. This suggests that restricting the inputs to a local region directly contributes to improved precision. Due to object symmetry, the yaw angle appears almost random across all models. However, for roll and pitch alignments, AnyPlace and RPDF achieve strong performance, where NSM performs relatively worse in both position and orientation. So these results quantitatively demonstrates that local region-based diffusion refinement is effectively for a high precision insertion task. So let's move on to the real-world evaluation results. So while all previous experiments were conducted in simulation, the key question at this stage is simple. So can a model trained purely on synthetic data operate effectively in the real world? To answer this, the authors evaluate the method across 16 different real-world placement configurations. For each scene, a single RGBD image is captured using a camera mounted on the Franca Amica robotic arms, and the model predicts placement pose based solely on that image. Looking first at the success rate. The evaluation focused on 3 multimodal tasks: the insert buyer, hang rings, and stack battery. Here's a mode. It refers to a distinct valid placement location for an object. So baseline model NSM fails on nearly all tasks, and RPD achieve partial success in some cases, but does not show consistent performance. In contrast, AnyPlace achieves the highest success rate across all these tasks. In particular, it reaches 30% success on a buyer insertion task, which requires high precision. So in the left side, the visualizations, the point cloud shows the placement pose predicted by the model. Below it, we see the real robot executing that predicted pose. Even in tasks requiring precise alignment, such as insertion and hanging, the robot succeeds consistently. This indicates that the low-level pose prediction model achieves sufficient geometric precision. And the right side illustrates multimodal pose prediction. It shows multiple possible placement locations predicted simultaneously within the same scene, which different colors represents different placement modes. So, like this. So regression-based models tends to operate over such multimodal structure, but AnyPlace avoids this collapse because the high-level VLM first separates the candidate placement location. As a result, the low-level model can perform precise refinement within each modes, enabling the system to capture multiple valid placements configuration without collapsing to the two unaveraged solutions. So this paper proposed a structured approach to object placements by explicitly separating the problem into mode explorations and precise alignments, rather than just treating it as a single complex pose regression task. So the first key contribution is the course-defined architecture. The VLM, Vision Language Model, first determines global placement nodes, and a local diffusion-based model then refines the pose with geometric precision. Importantly, the diffusion formulation allows the model to stably represent multimodal placement distribution. The second is the synthetic data engine. The authors automatically generate thousands of diverse objects and placements posed through procedural object creations and physics-based pose generation. This reduced the needs for real-world data collection while enabling the model to learn a bold and structured representation of placement. Finally, this design leads to strong real-world generalization. Despite being trained entirely on synthetic data, the model achieves an average success rate of 76% across 16 diverse real-world tasks into a zero-shot setting. This demonstrates that the system does not merely memorize specific tasks, but instead learn the structural concept of objects placement itself. So we can conclude by one sentence. By decomposing the placement problem into mode exploration and precise alignments, and combining VLM-based coarse reasoning with local geometric-based fine refinement, the model achieves robust real-world generalization using synthetic data alone. But they also have a limitation. First, although the model demonstrates strong performance in placement post prediction, the authors notes that performing a fully general pick and place pipeline at the same level of generality remains challenging. While the model can generalize placement post prediction, not every stable grasp can realize a given placement pose. In real-world setting, it is necessary to verify whether a pair of T-peak and T-place is executive. So resolving this through rejection sampling can be time-consuming and computationally expensive. In other words, although post-prediction generalize well, the execution policy is not yet fully generalized. So the second limitation is the lack of explicit modeling of contact interactions. The current system simply controls the robots to follow the predicted end effector pose. As a result, the robot may approach objects too aggressively, leading to the hard collisions or unstable contacts during placement. This issue is common in many rearrangement approaches. So, to address this, the author suggests integrating compliance control or force torque feedback, allowing the robot to adapt its motion reactively during contacts. And third, one is no language condition. Um, the current low-level model does not incorporate language conditioning. Therefore, it cannot distinguish between different placement types at the same physical locations. However, structurally, adding language input to the model would be straightforward, and the synthetic data generation pipeline could be extended to automatically produce diverse language conditions data. And another limitation concerns the quality of the input point clouds. The model's precision ultimately depends on the accuracy of the sensor data. So, in failure case, this one, the sparse point clouds of the rack leads to the misalignment in the ring hanging task. In peg insertions, unclear hole boundaries cause slight positional errors. In battery stacking, incomplete point clouds resulted in tilt placements. These examples demonstrates that even a geometrically precise model is constrained by sensor quality. So to improve this, the author suggests leveraging more accurate depth estimation methods, improving sensor quality, and developing reactive placement policies based on force and torque feedbacks for the final stage of placement. So, in conclusions, this paper presents an approach that reduces complexity and achieves generalizations. So key contribution lies in implicitly separating placement modes using a VLM and focusing on a local geometric information to predict prices CE pose. Moreover, the model demonstrates zero-shot generalization in real-world settings despite being trained purely on synthetic data. With that, I conclude the presentation. Thank you for listening.